Good morning all. So today's session we're going to see the behavior of RL and RC series circuit if they are connected in a single phase AC system. So let us consider the single phase AC system with series RL element RL circuit if it is there. So to understand the behavior of this RL series circuit if it is connected to this AC system, so let us consider the elements R and the inductor which are connected in series, and to this RL element the AC supply has provided. So this is V, and I can say whenever the voltage is applied the current is flowing through this circuit. So this is well known to us. And if you talk what could be, so here if you see the diagram, so I can write, so whenever this current I is flowing through the resistance and inductors, so they are going to give some drops here. So the drop is VR, is the drop across the resistance, and VL is the drop across the inductor. So that is what I assumed from this diagram. So if I let us consider, we have to, in order to draw this vector form or phasor form of this network, so I will take the current waveform. I will take the current waveform as my reference. I will take the current waveform as reference, and I am only concentrating on if it is a purely inductive capacitor, if it is a purely resistive circuit. If it is a purely resistive circuit, then what is the relation between VR and I? If it is a purely resistive circuit, what is the relation between VR and I? Is your VR is in phase. Your VR is in phase with current. This VR is, the voltage is in phase with current. You know, if it is a purely resistive circuit, then your voltage and current are in phase. So there is the magnitude, you can say VR. So this is nothing but drop. I can write V into I into R. R is the drop. Similarly, if you want to draw the phasor diagram individually for this inductor, and inductor, the voltage across the inductor is VL, and this is the I current is flowing through this inductor. So if it is a purely inductive system, then what is the relation between your current and voltage? So here my current lags voltage by 90 degrees. That is also we have seen in the previous class. If it is my pure inductor, then the current lags voltage by 90 degrees. So according to that statement, where my VL will come here, so my VL will come somewhere here, I can write. So this is my VL, that is also equal to I into XL. This is the drop across the inductor. Now see here, it is nothing but is going in counterclockwise direction, my rotors. So my voltage is leading, or my voltage leading by a 90 degrees, you can say 90 degrees to the current, or you can say my current lags voltage by 90 degrees if it is a, only if you talking alone with inductor. If it is a, specifically talk about the resistor, then this is what V and I are in phase. Suppose if you want to find, add these vector diagrams here, what is this VR vector and VL vector? So this is going to give us, this is nothing but your supply voltage V, this one, this is nothing but this V, or this is also can written as I into Z, where Z is called a impedance. What is this impedance? We will see later. So this is V is equal to I into Z. Now if you see, with respect to this current vector, my supply voltage making some angle here, that angle I can take is pi. So pi is the angle as between your voltage, supply voltage, and this current I. So if you talk here, in case of RL circuit, in case of this RL circuit, if you talk, what is the behavior of V and I here? So I can write my voltage lead current by angle of pi. My current leads voltage, my voltage leads current by angle of pi. Otherwise, my current lags voltage by an angle of pi. So that is the meaning. So this is my reference current. With respect to this reference current, this voltage has gone ahead of the angle of pi. So this voltage leads a current by pi, or my current lags voltage by pi. So it is the case in case of your if it is a RL circuit. It is a RL circuit, then there is a current lags voltage by some angle pi. But if it is a purely inductive circuit, there my current lags voltage by 90 degrees. So that is what the information you need to understand here. So if you take this vectorial form here, and if you want to find what is V here, then I can write this is VR square into VL square. Simply the square of the two vectorial forms. So I can write this is nothing but again IR square plus I into XL square I can write. Otherwise I can write this is again, if you make it I is outside, so R square plus XL square, or you can say I into Z. So this is it VI into Z, where Z is called root of R square plus XL square, and it is called a impedance of the circuit. Impedance of the circuit. It is called the impedance of the circuit, and because this R and XL are in ohm, so this is also in ohm. This is also measured in ohms. So that is what. From this triangle, again, you take this triangle, again I want to find what is the tan pi. What is the tan pi? Then I can write this opposite by this opposite is vector, this is VL. So this is nothing but your VL by VR, adjacent VR, or it is can be written as IXL by IR is equal to, I can write XL by R, XL by R, I can write XL by R, or further I can write this one. So pi is equal to tan inverse of XL by R, otherwise tan inverse of, instead of XL I can write WL by R. So this is the relation you also know, XL is equal to WL, where XL is equal to 2 pi FL. So there are the different relations we know. So this is, and from this information, if you draw what is the relation between R, XL and Z in a vector in a diagram format, so this is, I can write this is R, this is nothing but my XL, and this is nothing but my Z. This is nothing but my Z, or Z is nothing but under root of square R square for XL square. So this is we are getting, and this is the angle is called the pi, and this diagram is called the impedance angle, impedance triangle, impedance triangle. This diagram is called impedance triangle. And what is the significance of this impedance triangle is, suppose if you know R and XL, you can able to find what is Z. Otherwise, if you know Z and R and pi, you can able to find XL. So to find the different parameters, you can use this impedance angle. Now we'll calculate the power. What is the power consumed by this RL series circuit? So to calculate this power, so what I am going to take is, what is the instantaneous voltage we have? V is equal to Vm sine omega t. So this is we have to take as a reference. Now we'll take this is a reference, and my I is nothing but Im sine omega t minus pi. So why I'm getting this minus pi here? So because here the angle between your voltage and current, the angle between your voltage and current is your angle between the voltage and current is pi, isn't it? This is between your voltage and current is pi, where my current lags voltage by pi angle. My current lags voltage by pi angles. To satisfy that condition, I am writing Im is sin omega t minus pi, my t minus pi. So this is the equation I am writing for V and I, instantaneous current and instantaneous power. Now if you write what is the instantaneous power here, so this is nothing but I. So I can write Vm sine omega t and Im sine omega t minus pi. So these are the two equations. If you simplify this one, you're going to get Vm Im by 2 into cos pi minus cos of 2 omega t minus pi. So this is the term you are going to get. So further, if you just separate these two terms, then Im by Im, Vm by Im cos pi and minus Vm by Im by 2 cos of 2 omega t minus pi. So this is, I can say this is a constant term, because this is does not varying with the time, but this is not a constant time, it is varying with the time. But here my frequency is double the frequency. My frequency is double the frequency. It means my power is oscillating with a twice the fundamental frequency. That is what is that meaning? We have already seen in the case. Now we'll calculate the average power. Now we'll see what is the average power calculation now. So we'll calculate this one now. So this average power you can calculate as some 1 by 2 pi into integration 0 to 2 pi and this p d omega t. So this is the equation. If substitute these values here, 2 pi integration 2 to 2 pi, this is Vm Im by 2 cos pi into d omega t minus and again Vm Im by 2 cos 2 omega t minus pi. So this is what you are going to get, d omega t, something like this. So if you do the integration of this part, so this is the constant term. So this is the constant term. If you do the integration, the integration of constant term, this is going to get Vm Im by 2 cos pi you will get. But when comes to this one, if you do this one, this is going to get the 0 part. So I can write again this one, Vm by root 2 into Im by root 2 into cos pi. I can write like this. So here you can write finally this power is equal to Vm by root 2 is nothing but Vrms, Irms and the cos pi, where this is called a multiplication factor. Cos pi is nothing but a multiplying factor or factor which is multiplying with your voltage and current. So this is called a power factor. Power factor is multiplying with your voltage and current. So P is equal to VI cos pi. So this is the power measured by the wattmeter VI with multiplying a power factor. So this is what. If you draw the sinusoidal waveform, that instantaneous voltage and current and instantaneous power waveforms for this series RL circuit, then we know this. This is what we know. So this is the from I will show this. V is equal to Vm sin omega t is there, and I is equal to Im sin omega t minus pi. So this is the what we have. This is omega t minus pi, isn't it? Let me to recall. Yeah, this one. Im sin omega t minus pi. So these are the two instantaneous voltages. Now draw these diagrams here. So this is my voltage is reference I'm taking. So this is going from this one, and this is what my voltage is coming like this. And come to this current waveform. This current waveform is I can say this is the pi by 2. This is pi and this is 2 pi, something like that. But my angle pi may be somewhere here. So I can say this is the pi angle pi. So my thing will start from my current will start from this point. So it's coming like this. It's going like this. So this is what my things is this current waveform is going. So this is my current waveform. Now I want to write the instantaneous power here. So this instantaneous power is I can take here the instantaneous power. So if you see the things here, so this is what my current is going in this direction as well, isn't it? It is in negative direction as well. So if you see at this moment, only the current is in negative direction, but my voltage is in positive direction. So the product of these two I can take, it is the power which is in negative direction. And when come to this, from this point to this point, my current and voltage both are in positive direction. So the product of this both positive quantities, this is my current, and from this point, so this is my power. Again for these two, both are in the negative direction. So negative product of the both the negative, again you will get that positive point here. So this is what the power waveform you are going to get. So this is what the power waveform you are going to get. This is the instantaneous power, you can say V into I. So what we observed from this diagram here is, suppose this is my pi, isn't it? This is my pi. If I increase the pi, angle, that is pi angle, it means the negative area of this power will going to increase. So therefore my average power is going to decrease. Because the average power is nothing but the negative cycle and positive, this positive cycle and negative cycle of the area under the positive cycle and area under the negative cycle by the total period. That is the average point we are doing. So if you increase the pi, then the area under the negative cycle will increase, so that obviously my average is going to decrease. So that is what the meaning of this one. So if you have, how we are increasing this pi. So as we know this, we know what is the equation we know from what is the pi here. So pi is nothing but tan inverse of this omega L by R. So this is what the expression we have seen in the earlier class here, this one, right, or this one. It means how this pi is going to increase here is how the pi is going to increase here. So if my inductor is increases, if my inductor will increases, so if my inductor will increases, so obviously my pi also increases. As my inductor will increases, therefore I can say this negative value is going to increases. So therefore there is the average power may be reduced. So these are the different context you can understand this concept. So and again we know this P, this power is nothing but this I into VI into cos pi. So I can write this is what is V means I can write I into Z and this is I. So instead of cos pi from this this impedance triangle, instead of cos pi I can write, instead of this cos pi I can write r by z. So if you do this one, so you're going to get the z will going to cancel, I square r. So this is called the loss, this is called that power loss or consumed by a resistor, loss or power consumed by resistor. So I can give some point here. So what I observed from here is the actual power is consumed by whatever the power which is produced here, that is the average power, that is Vi cos pi is consumed by resistor, and inductor never consumes, and inductor never consumed the power. Why inductor is never consumed power? Because you already have seen. So for the inductor, so inductor for quarter cycle it will takes the energy, for another quarter cycle it will supply the energy. So average power consumption by inductor is 0, but my capacitor, sorry, my resistor will consume the active power. So that is what the conclusion we came from this analysis. Now we'll go for the second concept, that is single phase AC series RC circuit. Now we will see what is the behavior of this circuit. So let us consider a resistance which is connected to the capacitor in series to this resistance RC circuit. For this RC circuit, so this is what the voltage has, the AC voltage has provided. So this is what the current flowing through your this particular circuit. So whatever the drop which is occur across this source voltage, this resistor across this drop is VR, and the capacitor drop is VC, I can assume. This is VI and IR. So now I will draw the phasor diagram by only taking individual elements. I will assume that I only have a pure resistive element, and what could be my current and voltage behavior. That kind of thing you have already seen it. Again we will draw this phasor diagram by assuming individual R and C elements here. So first what I am going to do is I will take my current as reference. I will take my current as reference, assumed here. I take my current as reference here, and what I am trying to do here is I want to draw the vector diagram between this VR and I, because if it is a pure resistive circuit, there in that case my VR and I are in phase. So my VR and I are in phase, so I can say, so this could be my, VR vector, you can say this is my VR vector or IR drop. Now we'll come back to this only a capacitor. if you assume if it is a purely capacitor system, then your current then your current and voltage relation, here your current leads voltage by 90 degrees, or your voltage lags current by a 90 degrees. So my voltage Vc, that is I into Xc, this voltage Vc lags current by a 90 degrees. So this is the 90 degrees. If your vector is rotating in anti-clockwise direction, so anti-clockwise direction, so my Vc, that is voltage, is lagging 90 degrees with respect to my current vector. Now if you add these two vectors here, if you add your Vr vector and Vc vector, so this is going to give us a supply voltage V. This is I into Z. So this is what the information we are getting from this vector diagram. So I can take V is equal to, if we want to find what is V here, it is nothing but simply the under root square of Vr square and Vc square, because these are the vectors multiplication. So we want to find what is this V. So Vr square by Vc square under root, if you do that vectorial multiplication, then you will get able to get the things here. So IR square and I X is square also you can write. So this is nothing but again it's coming like R square plus X is square, or I can say I into, it is a Z. Z is nothing but again it is a impedance Z R square by plus X is square. Now again I can find what could be my tan pi, because this is making some angle here, right? So this is making some angle pi also, isn't it? Pi. So in between your supply voltage and current, there is angle between, there is angle, that is pi here. So what is the tan pi I can write here is, it is by seeing this triangular wave, this diagram, Vc by Vr is equal to Ixc by Ir. So this is opposite by that adjacent, that kind of thing. We are using this formula. So from this I can write Xc by R. Xc by R you can write, or sometimes Xc is equal to, you can take Wc, or 1 by 2 pi Fc. So there are different things we have. So you can also write something like 1 by WCR. This is also some relation you can write. So you want to draw the impedance diagram for this, then this is the impedance diagram you are getting. This is R, this is Xc, and this is the angle between this pi, and this is nothing but this hypothesis has the Z. This is called the impedance triangle. Okay, and if you want to see the what is the relation between your supply voltage and this current, if it is the RC circuit, then I can say that your voltage lags current by pi angle. Otherwise my current lead voltage by pi angle. You can say in case of RC circuit, my supply voltage lags this current by pi angle. Otherwise my current leads this voltage by pi angle. So this is what the conclusion I getting from this diagram. So I can write here, or I can observe the point, my supply voltage V lags current by pi angle. Otherwise my current leads this supply voltage by pi angle. So this is the observation I made here. Now we'll go to write what is the instantaneous current and instantaneous voltage. We know the instantaneous voltage, this is nothing but Vm sin omega t. So Vm sin omega t I am taking, because this is nothing but I am taking as a reference quantity. That's why sine omega, but this sine wave will start from the 0 point. But what about my current here? Because my current is leads by some angle pi, so I can write this equation to satisfy that point. Sine omega t plus pi, so this is going to satisfying these conditions, my this instantaneous voltage and current. So here my current leads voltage by a pi angle, my current leads voltage by a pi angle, so that is the meaning. Now come here, we'll see what it could be the instantaneous power. We'll see this one now. You know this V is nothing but I, V into I. Again the same thing operation we have to do here. Im by Vm by Im 2 and 2. So these are the multiplication I'm doing here. I can write, and sine omega t into omega t plus pi. So these are the things you can get. So Vm Im by 2, again cos pi minus cos of 2 omega t. This is the some trigonometrical formula. So 2 cos A cos B, some kind of, so cos A plus cos minus cos B, some kind of formulas we are applying here to solve this one. So if you not remembering these trigonometrical formulas, so once again you just try to recall all the trigonometrical concept here. 1 by 2 and cos pi I can write. This is coming here, Im by 2 cos of 2 omega t plus pi. Again it is double the frequency, you can say it is double the frequency, and this is varying with respect to time as well, but this is nothing but a constant term. There is no varying time, this is a constant term, you can say it's a constant term. Now let's calculate the average power. Calculate the P average power for this. So we'll do this one now and we'll see how we are getting. So the P average is nothing but 1 by 2 pi into 0 to 2 pi. Again substitute this instantaneous power here. So Vm Im by 2 cos pi minus Vm Im by 2 cos 2 omega t plus pi, and this is d omega t, something like this coming. So integration if you do, this is the constant part, so this is going to come something like this, P average which is coming Im, Vm and Im, this is by 2 cos pi will come, but integration of this part is going to become a 0. If you try to do this one, you will get the 0 point, that one. So this I can write Vm by root 2 and Im by root 2 into cos pi. So again my P average, that is coming Vi cos pi. So that is what the thing I'm getting here. Again if you take this power P average and if you write, this is I into Z, this is I. What is this cos pi is, again go back and get the triangle, impedance triangle R, XC and Z, this is pi. So cos pi you can write here, cos pi is nothing but R by Z. Want to calculate the cos pi, so this is getting R by Z. Again this P is coming I square R. It means your power consumption only because of this resistance. So that is the meaning of this P I square R we are getting. So you can write now again, note here. So this is the power consumption is because of the resistance, and there is no power consumption by your capacitor, because for the capacitor, so first quarter of cycle it is going to take the energy another quarter cycle, it is supplies the energy. So this because of the reason this is won't this capacitor does not consumes any energy, but your power this resistor will going to consume the energy, or it is going to absorb the energy. And the equation is P is equal to I square R, or P is equal to VI cos pi. Now let me draw the this instantaneous power waveforms here. This instantaneous power waveforms here. If you draw the instantaneous power waveforms, so I'm taking this instantaneous this voltage waveform, this one. So this is V. I can say Vm sine omega t. This is the reference I'm taking. But what about my current waveform? Current waveform is nothing but I is equal to Im sine omega t plus pi, isn't it? This is plus pi. It means it is advanced with some angle pi here. So this is what my current going something like this, going like this and coming like this. So this is what my current I. So it is having some angle here. So that angle I can, that is the angle is coming here. This angle is nothing but a pi. This angle is nothing but a pi, which is leading. Your current I is leading voltage by angle of pi. So that is the meaning. Now if you want to calculate what is instantaneous power, V into I, the product of these two. If you do the product of these two here, so what you are going to get if you take this point here from this point. So from this point both are in positive direction. So this is what my power coming. But when comes to from here to here, both are this is coming in positive, but my voltage is in positive direction and my current is in negative direction. The product of this positive and negative is coming like this. And again for this both are in negative down, and product of the two negative polarities is positive. Same thing you are going to do, and this is what my power is coming. My power is coming something like this. So this is my power. You can say this is my power. So here what the observation we made here, again if you increase the pi, if you increase this pi, so actually increasing pi means you are increasing the capacitance. If you increase the capacitance, then what happens is the negative area of this power, this P average, the negative area, this whatever the negative area we have, this is going to increase. This is going to increase. Therefore, my P average is decreases. My P average will going to decreases. So that is the point you can try to understand here. So this is what the theoretical concept you might have gone through this for your series RC circuit, and we will see some numericals on this series RC circuit, so that you can get some very clear clarity. Take the numerical here. A voltage of 125 volts at 60 hertz is applied across a non-inductive resistor connected in series with condenser. The current in the circuit the current in the circuit is 2.2 amperes, and the power loss in the circuit in the resistor is 96.8 watt. Now they are asking to calculate what is R and what is the capacitor and what is the resistor. So this is what the question is given to us. So this is the diagram. If you draw, what is the meaning of this? This is R and this is C, and this is the current is given here. I is equal to 2.2 amperes, and this is the 125 volts is given, and 50 hertz is given. 50 hertz is given. So this is what. So I want to find what is R value and what is C value. So this is what. So you know what is the power loss is given to us. This is 96.8 watt. Our P is equal to, we also know, I square R. This is nothing but 96.8. From this I can write 96.8 by what is this I? I is the 2.2 square. So this is what we are going to get, 20 ohms. Similarly, what is the Z here? V by I. This is nothing but 125 by 2.2. So this is 56.82 ohms. If you want to calculate what is this relation here, R square plus XC square relation. So I want to calculate what is XC here. So that is Z square minus R square. Now do this one, then you will get the X is equal to 53.2 ohms. But you know X is nothing but 1 by omega C, or it is 1 by 2 pi FC, or you can write C is equal to 1 by, what is 2 pi, what is F here, 60 hertz into what is this C. We are getting what is we want this what is XC here. So I want to find what is the XC. So this is nothing but, again we are getting 2 pi into 60 into 53.2. If you do this, you are getting 50 microfarad. So this is how you can solve this question or this numerical. So I'm trying to taking all the relations which has we have derived from earlier classes and this classes, and I'm trying to solve the I'm trying to solving the question. Now take the another question here. A series RC circuit takes power of 7000 watt when connected to 200 volts 50 hertz supply. The voltage across the resistor there is 130 volts. Now they are asking to calculate what is R, what is the power factor, and what is the capacitor, what is the equation for your instantaneous current and instantaneous voltage. These are they are asking to calculate. So this is, this is my capacitor. Again, this is the diagram. So 200 volts is given, 50 hertz. and this is the only voltage across the resistor has given. This is VR is given. We don't know what may be the VC here, and power is given. The power loss P is equal to given 7000 watt. So VR is given. This is 130 volt. So what is I'm trying to do here is, if you want to find what could be this instantaneous power, so I can write this is nothing but 200 into root 2 sine omega 2 pi ft. So 2 pi 50 into t, if you write, then this is you are going to get 282.84 sine 314 t. So this is what you are going to get. So we also know what is the power. Power is nothing but vi cos pi, vi cos pi. So again I can take some many relations. So r by z, or you can write this is nothing but I r by I z. So it is nothing but vr by v. So these are the different relations I am taking from. It is r, then this is my t, this is pi, z and xl. If it is my another triangle, impedance triangle, then this is z, this is xc, and this is r. So this is pi. So these are different angles we have. So what is this cos pi? So what is VR here? This is 130 by 200. If you do, then this is getting 0.65 cos pi. Cos pi you are getting 0.6 pi. It is a leading because it is a inductive, it is capacitive property circuit. So always your power factor is leads because your voltage, your current leads voltage. So that's why it is lead. And you can write I is equal to P by V cos pi. P is equal to 7000 by 200 into 0.65. So you will get the current is 53,846 amperes. So like that, so many relations we have. Use those relations, and what the parameter they are asking, you can easily calculate. So this is what I am doing here. So 53.846 and 2.41 ohms. And if you want to calculate Z, you know this is the relation, right? X into XC relation. So you can find RV by I relation, you know. So Z will get 3.714 relation, this value. Then if you want to calculate XC, then this is the thing, you know, 1 by R square by Z square by R square. So if you substitute those values, you are going to get this is the answer. Something like if you want to calculate X is equal to 1 by 2 pi FC, and I want to calculate what is C, then this is nothing but 2 pi F into XC. Now substitute these values, whatever the values we have got, then this is going to come 1126 microfarad. This is what we are getting. If you want to calculate what is pi, then this is cos inverse of 0.65. So you are going to get 49.46 angle. So this is in degrees. If you want to convert into radians, so this can be converted into radians by taking pi by 180. This is nothing but 0.275 pi. It is in radians now. Then what is the instantaneous current I can write here? It is nothing but Im sine omega t plus pi, isn't it? This is what. So what is Im? I can write, I can take this is Im 53.846 into root 2 sine of 2 pi ft plus 0.275 pi. So this kind of things you have to do this one. Simplify this. You are going to get 76.15 sine into 100 t plus 0.295 pi. So this is the instantaneous current equation, and this is the instantaneous voltage equation we are getting. We have found this one, this one, this one, this, everything we have answered in this question. So this is the way you can calculate any kind of network, and I hope in this class you have understood what is that series RL and what is meant by series RC circuit.